Okay, so today's video is going to be about something very interesting. Before I before telling, let me just write the topic name. Okay, so we will be talking about quantum quantum electrodynamics. Okay, in quantum electrodynamics, let me just get started with, because this whole thing is based on a single phenomena, electrodynamics. Okay, and this whole thing depends on one single phenomena, which is in magnetism and in electromagnetism, electric field. So what we will talking about in electric field is this. We know that in electric field, if we have two positive or two like charges, let's suppose electrons, and they move closer to each other, they're moving closer to each other, we know that the moment they will come close to each other at certain distance, they will repel. Okay, they will repel. Repel. This is a L, not a K. In so we are no we have been said that till now this all is because of the force, some kind of force, electromagnetic force or electric force, how I say this, they repel. Okay, because of them being like charges. That's true, like charges they are, like charges. That's true, they are like charges. But this topic, electrodynamics, quantum electrodynamics, is one of the accurate way to explain how what actually happens. Okay, this is classical physics. Classical, sorry, classical physics. Okay, now let's get to quantum physics. How quantum physics defines the phenomena, especially Feynman, because what we have here is Feynman's diagrams. Feynman Feynman's diagrams. Okay, and it's such accurate. That's one of the incredible accurate phenomena or explanation we have for this, them going away from each other. So what Feynman's diagram says is that when two particles are coming close to each other, let's suppose these electrons, when they are coming close to each other, the point they come close to each other, what happens is that in between they experience not electron, gamma change or photon change. Okay, what that photon change causes that it will give them a like a third for this will become as this will act as a opposite force. That exchange will act as a force which will push the electrons away from each other. How I will say in terms of Feynman's diagram is that if, let's suppose, if we have yeah, over here, if we have a particle here and a particle here. Okay, so what will happen is that if this particle is coming towards this side and there's a particle coming from this side, the moment this particle will come close, it will release photon, and this photon for this particle over here, it will act as a backward force as it released. Okay, it went there, opposite direction, and the moment this photon will be absorbed by this electron, which is coming over here right now, is right now absorb. What will happen is that this electron will move in the other direction. Okay. So this is how Feynman's diagram is explaining how what actually happens. Okay. So if let's suppose we have two particles which go like this, which go in this direction, one is from here till here, second from here till here, and they're moving, they both are moving. The moment these two reach this point, electron is exchanged, or not electron, photon is exchanged, and that causes this electron to move in this direction and this electron to move in this direction. So it looks like they are going away from each other. Well, they are going away. That's not the problem here. So then, but then there are some rules the Feynman diagrams have to follow. Okay, one of the things is that three things you need to know about the Feynman diagrams. One is the arrows, lines and arrows. Okay, line and arrows. Second is about the fundamental particles. Okay, and the last of them all about energy conservation. Okay, conservation and so on. Okay, so what we don't need to know about lines and arrows is that each like let's suppose if you have if I draw like line like this with an arrow, or for the arrow it's a little later call. This line over here shows that it is a, what do you call that, an electron. Okay, it's not electron, it's a fermion. And a dotted line, I didn't draw a dotted line, but this is how it should be a dotted line, and dotted line represents what do you call that, photons, or not photons, W and Z bosons, which photon is part of bosons, so yes. And then we have then gluons. These are gluons. We'll not talk about gluons that much. We will only focus on the first two in this one. We will focus on these two. Okay, these will be our main. These are gluons. Okay, and yeah. So then what we need to know is that the arrows, these arrows, the one I highlighted, arrows, they have their direction matters. Okay, what I mean by their direction matters is, wait, let me tell you. Zoom in. Sorry. So what I mean by their direction matters is, if I draw a space-time graph, this is a time, and this is space. Okay, so what these arrows represent is that if they are going increasing in time, they have a increasing gradient that will be they will be particles, they will be matters. They will be used for matters. And what's the opposite of a matter? Antimatter, right? So those arrows which decrease in which have a decreasing gradient, we say for them that they are for antimatter. Okay, so then about one more, yeah, so then about the fundamental particles. Remember that in the standard model or a standard model of particles, in that there are multiple fields: fermions, bosons, then we have leptons, and I think more as well. But we will be talking about fermion and bosons in this our Feynman's experiment. Okay, so when we include fermion and boson, I will not give that much detail about this part topic, but just know that these are the fundamental particles we will be talking about in our these rules. Then comes the energy conservation. What about energy conservation? Why is energy conservation important? Energy conservation important. Okay, so we know that when a process is done, let me just go a little into classical physics. In classical physics, if we have two cars, okay, they're coming into each other, their momentum or their energy and momentum, their momentum and energy are conserved. Conserved means their energy and momentum will equal after and before. What was the energy before will equal our energy after, as well as the momentum before will equal momentum after. Okay, so keeping that in mind, in QED it's the same thing. Let's suppose I will make a new diagram of Feynman diagram. This is one new diagram, and and let me go with this one. And so keeping them, remember we were talking, let me just, to make it easier, let me just draw it in a space-time graph, space and time. And so this will be an increasing, so it's a particle, decreasing, it's an antiparticle. So in this case it will be electron, a positron electron. This one is increasing, so E negative, decreasing, E positive. Okay, so now this is, what is this? This is gamma, photon. Okay, so what we need to focus on is, in this what's happening is, or to, okay, let's make it more simple. This over here, they both collide and give off photon, right? Or this can also be written as a photon, sorry, not a photon, yeah, it is a photon. For now simplicity, I'll just draw it like this. A photon and an electron can combine to give a positron. Okay, here what is this electron? This is photon, and this is over here. So the main thing here will be that the momentum or the energy should be conserved. The energy should be conserved such that over here, when we focus over here, E negative is these are fermions, right? And fermions have charges either, so this electron will have -1 and the positron will have +1. So -1 +1 equals 0, and as well as a photon. Photon is a boson, it doesn't have charge, so it is a 0. So that means 0 equals 0, so energy is conserved. That means a diagram can be, the Feynman's diagram can be in any form, but the main condition is that they have to have conserved uh, energy and momentum. So their momentum and energy should be conserved. Other than that, you can have the Feynman diagram in many ways. There are many different diagrams for it, but each increases with complexity. This is one of the common one. Then we also have this as well. This is one more diagram. This is one more diagram we have. By the way, these over here at each point, these dots, these common points over here, we call these vertices. We call them vertices. Okay, and their point of interest as well. So what happens is, over here same thing, a photon is released, photon exchange happens, the one particle moves in this direction, this particle moves in this direction, as the same thing as saying when two electrons come closer to each other, they experience repulsion, and that repulsion is nothing but this photon exchange. Sorry, this is a photon change. And in terms of simplicity, this is how it looks like: particle, electron, and an electron coming closer to each other. The moment at this point they go away from each other. Repulsion. Okay, this is what is happening here. That's one of the best ways to describe how this works. This is known as quantum electrodynamics. And in this, there are many Feynman diagrams which we can have depending on how we use it. Let's suppose we can have, for now I'll just give examples of Feynman diagram. Example. We'll not talk about them, we'll just give example of Feynman's graph, Feynman diagram. Okay. Wait, how can I go with this? So what we have here, we have one, we already, this is one of the common one. Then we have this, and we also have this. This is one not one important one, but yeah. So here, let me just highlight this. Okay. So then, what else do we have here? Not this will maybe it will cause errors. So energy and momentum are conserved. Many outcomes are possible. As I said, we can rewrite a same Feynman can rewrite, depending on what we want, rewrite Feynman, or redraw I would say, diagram in many ways. Many ways. Okay. So relate photon to electron type particles. Okay. So the Feynman diagram can add up. Yes, it can add up. We know that when we talk about the probability of Feynman diagram, what would be the probability of Feynman diagrams is that they would have to equal 1. They could add up this constructively, because there are two types of adding in quantum mechanics: constructive and destructive. In constructive, let's suppose we have one, this is just an example, we have the vertices, Then we have this photon exchange, and here let's suppose we added with this one. We could also have one in this. Sorry. It's unnecessary. The electrons will always will go away from each other. There could be some chances that it will go into each other. Okay, and they could add up and create a particle, a certain particle. Okay, create something. Okay, as well as they could add up, or let me just write a different one. To save time, I'll not change color. And what else? One more. I need one more. Let's just go with the normal one. This one, this, and this. Sorry, not this, and this. So they could add up as well to give nothing. This is equal nothing. So this is destructive thingy. What do you call this? Destructive matching sum, destructive sum. Okay, so then these are examples of Feynman's diagram. So yeah, okay, so one important thing in Feynman's diagram is that when we superpose or superposition them, they give a certain probability. Okay, like what I was telling here, this alternative probability now, because what we are doing is we are trying to combine them, and when we don't look at them, they can be many Feynman diagram when not observed. Okay, so then many Feynman diagram when not observed, it can be in many. This is what you call superposition. This is what we have, constructive and destructive sum. Remember that all these vertices over here, they are 1 by 100th of a probability of the first one. So that means as vertices increase, increase 1 by 6, 1 by 10, 100 increase. So so what do you call this? So prob decreases as we go higher in difficulty, decreases. And that's one of the like important and simplicity of Feynman's diagram that we have is, so we know that as we increase the complexity of the diagram, that and vertices we increase the vertices, which also means complexity is increasing, that gives us the probability of that certain thing is more. So this reduces the answer to simplicity, because we don't have to look at complex Feynman diagrams. We can only focus on the simple one and get our preferred answer. So there are some Feynman diagrams. There are some Feynman diagrams which are known as loops. Okay, we have some Feynman diagrams which act as a loop. And what the loop does is, let's suppose we have these two and we have these. Okay, what do I mean by loops? Yeah, so what do I mean by loop is, sorry, it's a little bended. Let's suppose we have one scenario in which the photon is emitted. It creates, for some time, for a certain time, it creates a loop of antiparticle and particle and then re-emits. Okay, this is once for one loop. Second loop could be that at the point, starting point, as starting point, over here photon is emitted and then absorbed again. This is second point. Okay, then third loop is like this. It's vice versa of the first one. Okay, this is a second situation. Oh, sorry. This over here. In this one we will have at the bottom. Okay, so here we have loops. Photons are emitted and re-emitted at certain points. Okay, for simplicity I'll just curve it for more space. So then we have, what do we have now? Wait, let me just circle the this. Okay, let me just draw the arrows as well. So what we see is that what do you say? What do you call that? Sorry. What was it? What was it again? So, what was I talking about? Loops. Yeah. So we are talking about loops, right? So what I want to notice or focus on is, now we'll talk about the math behind it. The math behind this QED. Okay. QED. Now, when we talk about the math behind QED, there is something known as Lagrangian QED, and it's written as L equal lambda, sorry, not lambda, wave symbol, I gamma, this mu d small mu minus m. Okay, this is one, and then there's one more, which is this, which is minus 1 over 4 minus this is, I think it was on minus like this, there's something like this, and f this v, sorry, f u. Okay, let me just explain this equation now. Okay, so the focus here is there are two parts to this equation. Okay, there are two parts of this equation. This is the first part, this is the second part. Okay, so the first part here, okay, so first part here, in this I, this shows or has information on how the fermion will interact with photon, this photon. Okay, how fermion interacts with information, has information how fermion interacts with photon. Okay, and this is, again, we all know that what this is. This is a mass, this is mass, and this over here, my friends, lambda with a bar on the top is a wave function. We all know it's a wave function of antiparticle, because we have this in whole this our topic, we have some main things are antiparticles, right? Antiparticle and particle. So this is for antiparticle, and yes, you might have guessed it right. This particle, this one is for of particle or matter, not antiparticle, matter and antimatter. Okay, so if I write, like, if I want to write what this whole equation does, is that it shows the behavior. Equation shows, equation shows how electromagnetic force behaves. Okay, so, and over here this is something known as tensor. Okay, this one over here is a tensor. Okay,